JVC, Service and Engineering Company of America, presents Compact Disc Basics. This video was produced to teach a technician the basic concepts of compact disc. We will look at precautions in handling, what you should know before you open a CD player for service, the compact disc and CD basics, everything from disc specifications, analog to digital conversions, and more. The laser assembly design, construction, and theory, compact disc player designs, a look at various mechanisms and an in-depth study of CD player logic, and finally the CD startup sequence, a great outline of the startup process for CD players. Precautions and handling. There are special precautions that must be considered when servicing a CD player. The laser diode, also known as the Optima, produces a very intense and finely focused laser beam. Never look directly at the laser light. Direct exposure to the laser light can cause permanent eye damage or irritation to the skin. Although the user of the equipment would never be exposed to the laser, due to interlocks and mechanism design, the technician has the ability to override these interlocks and expose themselves to the laser when working on the mechanism. If you need to examine or look at the laser light, it can be done safely at an angle from at least 1 foot distance. This light can barely be seen by the human eye, but the laser usually glows when the light passes through the diffuser. The laser also emits electromagnetic radiation that is not harmful to you, but can damage sensitive devices such as magnetic medias or even some wristwatches. Cleaning the lens. The lens of a laser is either plastic or glass and should be cleaned gently with a soft lens cleaning cloth or an airbrush blower. If the lens is fogged over by some residue, it will require a lens cleaning kit. There are lens cleaning kits available where there is a cleaning disc with a liquid solution, or some manufacturers have a lens cleaning kit designed for technicians. If these kits are used, only dampen the swabs or brushes and clean the lens surface by wiping in circular motions from the center to the outside. Never use any other cleaning fluids because they can permanently damage the lens or penetrate the delicate mechanism and coils beneath the lens. The compact disc. The compact disc is similar to an old LP record where there is a continuous track of music. Each of these have a pickup device that reads the music from the disc or record. The LP record has a single groove, one on each side, that tracks from the outer edge of the record to the middle at a constant speed. In the record groove is a mechanical imprint of the music it produces. When the stylus travels through the groove and over these imprints, mechanical vibrations are produced and picked up by the stylus and converted to analog voltages. The LP record is subject to wear from old styluses and surface scratches, which can distort audio playback quality. In contrast, the CD does not have any grooves, is single-sided, and tracks from the inner edge of the disc to the outer edge of the disc, following a continuous row of pits that are pressed into the surface of the disc. The speed of the disc changes to maintain a continuous rate of data transfer. The laser pickup does not come in physical contact with the disc, but detects and follows the continuous row of pits as the beam of light from a laser passes over them. The laser's objective lens maintains a distance from the disc where it achieves the best light reflection called focus. Because the objective lens never comes in contact with the CD is not subject to wear. However, the CD is subject to other physical damage, such as scratches and warped discs. Most minor problems do not affect playback audio quality because of error correction techniques used and the focal point maintained beyond the surface of the disc. In the disc is a continuous row of pits lined with a reflective and protective surface. These pits represent digital data, audio, or video that is read from the disc by the laser reflecting off the surface of the disc and the surface of the pits. When the laser crosses over these pits, they produce a continuous output of ones and zeros, which are later used to produce the playback audio and video. There are several systems used which allow the laser to track the data path, following the continuous curve in either forward or reverse. This method of following the data path is called tracking. We will be looking at a 3-beam system in this video. The CD master disc is made from mechanical or electrical processes. Then a metal master plate is created and used during the manufacturing process. The metal master plate is used to stamp pits into plastic polycarbonate discs. Next, a layer of reflective film and protective coating is applied to the top surface of the disc. The term pits refers to the imprint pressed into the disc, but appears as a raised surface to the laser side of the disc. Finally, the label is stamped onto the top side of the disc. The standard size compact disc is 120 millimeters in diameter. It has a center hole of 15 millimeters and is 1.2 millimeters thick. CD standards specify that the CD can contain up to 74 minutes and 33 seconds of audio information. However, it is possible to exceed this limit by varying some of the CD format specifications, and some disc manufacturers do, but it is not guaranteed to work on all CD systems because of design, programming, and cost factors of the unit. The table of contents, called TOC, is located in the lead-in area of the disc. This is a directory for the CD player for information such as the number of songs on the disc, the location of each song, how long the song is. The program area is where playback audio and video information is stored. The lead-out area is the indicator that the end of the program area has been reached. Here's a close-up of a compact disc. The track pitch is 1.6 micrometers, which is the distance between the row of pits. There are 9 pit lengths used, which are a result of an encoding process of the digital data called EFM, which we will look at later. The pit lengths range from 0.9 micrometers, which is 3 T-cycles long, to 3.3 micrometers long, which is 11 T-cycles long. These pits are 0.5 micrometers wide and 0.11 microns deep. The T-cycle is the clock rate used to read the data from the disk. 1 T-cycle equals 1 over 4.32 megahertz. This clock signal is called the bit clock. Analog to digital basics. When a CD is produced, the original analog audio signal is converted into a digital signal. In order to do this, we apply 2 processes, sample and hold and quantization. The original analog signal is first sampled at several points, and these sampled voltages are held long enough to convert the analog sampled voltage into a digital word. This conversion from analog voltage to a digital word is called quantization. A 16-bit word is produced for each sampled point. These 16 bits allow 65,000 different sampling levels to be produced. This higher resolution of sampling levels at a high sampling rate increases the dynamic range, signal-to-noise ratio, to about 98 dB, and reduces quantization noise during sound reproduction. The CD has a frequency range up to 20 kHz. Therefore, in order to reproduce the original audio signal for the CD, a minimum sampling frequency of 2 times 20 kHz is required. The sampling rate of 44.1 kHz was chosen for the CD, which is directly related to other clock rates used in the CD system. This 16-bit sampling at 44.1 kHz results in a high-quality digital recording. During the recording process, each 16-bit word is broken into two separate 8-bit words called symbol words. This allows for easier processing and reduces the cost in CD equipment design. These two symbol words then get sent to an error correction process before recording. Error correction. We will briefly look at the error correction concepts used in compact disc. There are three layers of error correction used: interleaving and deinterleaving, parity correction, and interpolation. The methods of error correction used during playback will vary depending on the design of the compact disc player. Because the digital information is stored in the form of pits on the disc, a dirty or scratched surface of the disc can obstruct the data from being read. Parity checking is applied to the data before it is recorded and can be used to recover from most errors. However, the compact disc technology uses several methods to restore the data before failing to do so. Interleaving and deinterleaving. Interleaving and deinterleaving is applied to the original 8-bit symbol words of audio information. This process generates two parity check words at different stages of the interleaving process. These parity words are called the Q parity and the P parity. Here we have a string of data. If the original data was recorded onto the disc in its original form like this, and a scratch on the disc covered a portion of it, data recovery would be difficult or impossible because large portions would have to be reconstructed. If we were to use an interleaving pattern to mix up the data before putting it onto the disc, we could reverse the interleaving pattern during playback. This deinterleaving process restores the data to its original form. If a scratch caused dropout, as you can see, the damage is less likely to prevent data recovery when we apply deinterleaving. The parity checking routines use the Q parity and the P parity and would have no problem in determining the missing information. The system used is called CIRC, Cross Interleave Reed-Solomon Code, which is several levels of parity checking and interleaving. Due to the complexity of CIRC, it will not be covered in this video. Interpolation. After deinterleaving and parity correction have failed to recover the data on the disc, interpolation is applied. Interpolation produces an average value between two known sampled values. There are cases where an error does not get detected or corrected by the error correction systems, and the result usually produces a click in the audio output when the muting circuit is turned on and off. EFM means 8 to 14 modulation. The original 8-bit data words were converted to a 14-bit data word during the recording process. This helped lower the frequency of transitions that occurred between ones and zeros on the disc, and to maximize the recording density on the disc. The EFM process is applied to the data words for every frame of data recorded onto the disc. The reasons for EFM encoding are: it increases recording density, which means more information can be packed onto the disc; reduces the recording bandwidth, means less transitions between ones and zeros; it allows the use of less expensive optics and simplifies the tracking process; it limits the playback frequency to 720 kHz; it reduces the DC current, which prevents generation of noise that affects CD servos. The logic used in EFM encoding is called non-return to zero. This simply means every time there is a 1, the output level is reversed and held there while there are zeros. It will hold this level until the next one occurs. In the EFM conversion process, a lookup table is used to convert an 8-bit word to a 14-bit word. An 8-bit word can produce 2 to the 8th or 256 combinations of ones and zeros. If we increase the word length to 14, 16,000 combinations of ones and zeros can be produced. 14-bit numbers are used because some combinations of ones and zeros in 8-bit words are difficult to distinguish as the laser reads them from the disk. This is because the laser can cover more than one data bit at a time. Therefore, some restrictions or rules have been developed to ensure that this does not occur. Our first rule of data encoding: there must be no less than 2 zeros between ones. This will remove the possibility that the laser light passes over 2 ones at any given time. Here is 2 14-bit words. Conversely, if there were not enough ones in the data stream, the laser would not have any data path to track and the laser would drift. We can see this in this simulation. So we have developed our next rule. There must be no more than 10 zeros between ones. These two rules are called the 2 to 10 rule. This leads us back to why we needed to convert the 8-bit words to 14-bit words. The original 8-bit word can produce only 256 combinations of ones and zeros. However, only 100 combinations meet the 2 to 10 rule. The 14-bit word can provide 270 combinations, and therefore can provide the 256 combinations needed. This is why 14-bit words were chosen. If we were to place two 14-bit words next to each other, there are combinations that would violate the 2 to 10 rule. Therefore, 3 bits called merging bits are inserted between each 14-bit word in any combination that maintains the 2 to 10 rule. These 3 bits have no meaning and are removed and discarded during playback. Frame format. The EFM data is stored on the disk in frames, which have exactly 588 bits of information each. Each frame is divided up to provide several types of information called words, which are used for CD operation. The types of words used are the synchronization word, the control word, audio and parity words. We will look at each of these in detail, beginning with the audio and parity words. As you recall, the original analog audio was converted to digital and broken up into 8-bit symbol words. After the CIRC interleaving process, the data for the frame is collected and grouped as follows. First, 12 8-bit symbol words, followed by 4 8-bit Q parity words, which were created by the CIRC, are followed by 12 more 8-bit symbol words, and finally 4 8-bit P parity words, also generated by the CIRC interleaving process. Once these 8-bit words have been collected, they are converted into 14-bit EFM data words. Each of these 14-bit words are separated by 3 merging bits each. The control word. The control word contains subcodes and display information which includes operational data such as the table of contents and track timing information. The control word is originally 8 bits long and is created while the audio information is being processed. However, you cannot store much information in only 8 bits. Therefore, the CD logic will collect the data from 98 frames at a time, put all the data together during playback. This is called a block of data and occurs 75 times a second. We will look at this block of data containing the subcode information shortly. Each original 8-bit control word is then converted to 14-bit EFM data, followed by 3 merging bits of its own. The synchronization word. After the control and display data and the audio information is formatted, the sync word is added onto the front of the frame. This sync word is a unique pattern where a 11T pattern is repeated 2 times to indicate the beginning of the frame and is used for disk speed control. The synchronization word is the first in the data stream when played back, but is actually the last piece of information put into the frame during the recording process. The synchronization word is 24 bits long and has 3 merging bits attached. The frame is now complete. Let's look at the breakdown of the data format. The sync word is 24 bits long plus 3 merging bits. The control and display word is 14 bits long plus 3 merging bits. There are 12 audio words, which are 168 bits plus 36 merging bits, 4 Q parity words, 12 more audio words, and 4 P parity words, for a total frame format of 588 bits. In order to read the 588 bits at 7.35 kilohertz, the frame rate, you need a bit clock at 588 times 7.35 kilohertz, which equals 4.3218 megahertz, the bit clock. You can now see a relationship between these clock rates developing. Now we will look at the format of the subcode block. During playback, the subcode block begins when the 8 bits of control data contain a sync pattern in 2 consecutive frames. This is called the block sync, which occurs once every 98 frames or at 75 times per second. The block sync is not the same as the frame sync and should not be confused. As the CD plays, the frames of data are processed by the data processor, which detects and separates the control and audio words. Contained in each control word, there are 8 subcode channels called P, Q, R, S, T, U, V, W. Only the P and Q channels are used in audio recordings. The R, S, T, U, V, W channels have been in use for video graphics, such as graphics used in karaoke and video graphic CD players. As the frames are processed, the subcodes P through W is collected for 98 frames. This creates a block of data 8 bits wide and 98 bits long. Once again, 98 frames at 7.35 kilohertz are collected to produce 75 blocks of subcode data per second. The first 2 bits of every subcode channel is part of a sync pattern. The remaining 96 bits of each subcode will depend on its purpose. The P channel is a control flag that is used to indicate the approach to a specified track. It is no longer used in modern CD players and is not utilized by JVC products. However, it is a 1 during the first few seconds before each track, the lead-in area, and to indicate a pause between tracks. Zeros are used during the music portions of the CD and alternate with 1s at the lead-out portion at the end of the disc. The Q channel is broken up into 4 fields, which contain very important information. These fields are called the control field, address field, Q data field, and a parity field for error correction for the Q channel data only. The control field is 4 bits long and indicates whether 2 or 4 channel preemphasis was used in the original recording process. If preemphasis was used, this field will enable a deemphasis circuit if one exists in the unit. This field can also indicate if copy protection is enabled, but this flag is generally not used because any protection schemes are done at the hardware and software level of the machine. The address field is 4 bits long and indicates how the following Q data is to be used. There are 4 modes used at this time. In Mode 1, the cue data contains information such as music numbers, music contents, minutes, seconds, frame, and index numbers. In Mode 2, the data contains a catalog number of the disc in a universal product code format. In Mode 3, the data contains ISRC, International Standard Recording Code, which indicates the country of origin, manufacturer, year of the recording, and the serial number of the disc. In Mode 4, the data contains information that is used in the video modes. The cue data is 72 bits long and is used according to the address modes just described. The most common one used is Mode 1 information that contains these data items when used as a read-in track, and these items when used as a read-out track. The CRC is 16-bit parity checking data used only for the cue subcode data channel. This should not be confused with the Q or P parity used in the frame fields. The data from channels R, S, T, U, V, and W are collected and used together for CD and TV graphics, video information, CD MIDI, and other future applications. These channels together provide one packet containing 4 information packs, 6 bits wide by 24 frames in each block of subcode data. Therefore, 4 packs of data is processed 75 times per second for a total of 300 packs of data per second. Now we will look at the fields contained in each pack. Bit 3 of channels R through W combined produces 2 3-bit words which indicate one of the 5 modes. Sound only mode. The graphic area is generally not used in this mode. Line graphics mode. This is for liquid crystal displays. The TV graphics mode. A user mode for business applications. And CD MIDI mode used in the musical instruments that support the MIDI data interface. Bit 4 of channels R through W combined produces a 6-bit word which provides several instructions to the graphic decoder of the CD player. Currently, there are 8 kinds of instructions used. These instructions give commands to the graphic processors to display special fonts, screen colors, borders, and other future specialized commands. The first of 2 parity fields used in each pack is the Q parity. Parity Q0 and Q1 are used for correcting errors in the mode item and instruction data fields only. The data field contains information required by the mode item selected and instructions above. The second of 2 parity fields used in each pack is the P parity. Parities P0 through P3 are used for the data field only. Do not confuse these parities with others used in different subcode channels or frame fields. This completes the explanation for the 8 subcode channels that are from the control and display word of the frame. Let us review the necessary signals used by every CD system. The bit clock, 4.3218 MHz, is the main clock used for processing the data read from the disk. Mostly all other clocks are derived from this clock. The frame sync, 7.35 kHz, indicates the beginning of a frame of 588 bits of data each. It is detected every time the 11T EFM data pattern appears 2 times consecutively. The block sync, 75 Hz, occurs every 98 frames. The block sync is detected when the first 2 frames of the 8-bit subcode data have the SO and S1 sync pattern. The audio was originally sampled at 44.1 kHz. Therefore, you can expect to see this clock signal, or some multiple of it, in the digital to analog processing areas of the circuits. The laser assembly. There are many generations of laser assemblies, also called optimas, that vary in construction but are basically the same. There are two basic systems, a single beam system and a three-beam system. We will cover an example of the three-beam system, which is more common in JVC products. In this illustration, the semiconductor laser emits a single beam of infrared light that has a wavelength of 780 nanometers and is barely visible to the human eye. This beam passes through diffraction grating, which splits the single beam into three beams, the main beam and two sub-beams. The two sub-beams are less in light strength and are used for the tracking servos. The main beam is used for reading the data and for the focus servos. These three beams are passed through a beam splitter, which separates the emitted beams, the beams going to the CD, from the reflected beams, the beams returning from the CD surface. The beams then travel through a collimator lens, which converts the three beams into parallel beams. The beams then pass through the objective lens, through the air, and strikes the disc surface. The laser light strikes the surface of the disc and focuses down to a spot about 1.7 micrometers in diameter. The distance from the surface of the disc to the reflective surface provides an important refractive element, a lens, in focusing the laser on the pits. This refractive element is created by the transparent plastic used and is the final element in the array of optics of the laser path. Because the laser light is focused down significantly, minor scratches or dirt on the disc surface does not affect the reading of the disc. When the three beams reach the pits on the disc, the three beams are not in a straight line due to the diffraction grating in the optima. The sub-beams are in front of and in back of the main beam and slightly offset to the left and to the right. As the disc spins, the laser follows the track of pits. When the emitted beams strike the flat reflective surface, they reflect back into the objective lens, through the collimator, and strike the surface of the beam splitter. Some light will get past the beam splitter but will cancel out. The majority of the beam is reflected off the beam splitter and passes through a cylindrical lens. This cylindrical lens changes the shape of the beams into an ellipse, which then goes to the photosensor array. As the beam passes over the pits in the disc, the photosensor current output changes depending on how much light is reflected back to the photosensors. This simulation shows that when the beam passes over a pit, minimum current is sensed at the photosensor. This is because the pit is 1/4 wavelength deeper than the surface of the disc and becomes 180 degrees out of phase and cancels itself out when reflected back. This reflection-no reflection results in creating the digital information by representing ones and zeros. Now we will look at compact disc designs. The CD player is divided into two distinct areas, the mechanical control section and the CD section. These sections will be explained and their functions will be described. The mechanical controller section. The mechanical controller section, called Mechacon, controls the mechanism that surrounds the CD assembly. This Mechacon can be designed to operate a portable single-disc unit or a 100-disc changer unit. Many units today don't have a tray or magazine at all. The disc is simply inserted into the mechanism. The Mechacon controls all mechanical functions and motor drive circuits. that perform disk loading, unloading, magazine detection, magazine tray selecting, cover open-close switches, and many other safety interlocks. The Mechacon communicates with the CD section only to give general instructions such as CD section power on-off control, track changes, pause, stop, search, etc. It receives data back from the CD section, which includes data such as the table of contents information, track, minutes, seconds, etc. Because many features of the Mechacon vary with the type of mechanism used, a general description will be given, which can be applied to servicing any type of CD mechanism. We will now give a general description of mechanism-controlled motors, switches, and sensors for CD operation, because troubleshooting begins by learning to identify the various devices used in mechanisms and the Mechacon logic. In this 100 disc changer, we will look at a vertical motor, also called lift motor. Its purpose is to move the mechanism up and down to select a magazine tray. These are usually found in multi-disc units. To sense the position of the vertical lift, in this unit a photosensor is used to detect the slots on an encoder rail. Some units use a switch. Once the mechanism is reset, it usually counts and records its current position. If the Mechacon has problems locating a position, it will usually perform a reset and begin again. The horizontal or tray motor moves the trays in or out of the magazine and places the disc in position over and onto the spindle motor platter. This particular mechanism has two horizontal motors with belt drives mounted on the vertical lift. The horizontal position is detected by a switch or a sensor when the tray is fully loaded in the mechanism or unloaded in the magazine. It is also used to detect the start and finish of the loading-unloading process. Common names for these switches are loaded-unloaded, start-finish, or tray in and out switches. Sometimes two or more of these switches or a separate switch or sensor are used to detect mechanism rest or home position. When the mechanism is reset, the mechanism will cycle and stop at the rest position. It may then proceed with the next selected operation. This unit has a laser position detect switch because the laser moves between sides A and B. So far, we looked at several mechanical switches that are commonly found in a mechanism. Other switches and sensors you will find in other types of mechanisms are a magazine detect eject switch. This switch will detect if a magazine is loaded or not present in the mechanism. In units that have a single disc or tray, it's sometimes called the eject switch. A jab switch. Before a different tray is selected, the tray at the current position is checked to make sure it is placed completely inside the magazine. This action of the horizontal motor produces a jabbing action towards the magazine. When the jab switch is detected, the next tray can then be selected. A door open-close switch. This is generally a safety interlock to make sure the cover is closed on portable type players. In many units, the door must be closed to clamp the disc down onto the spindle platter. And one other switch not covered was the rest home switch. All CD players have a rest switch, which indicates when the pickup is at the inside or center of the disc. This is usually mounted on the pickup assembly. We will now go on to the CD section. The CD section is responsible only for providing playback and drive of the disc currently mounted. The CD servo processor communicates with the Mechacon circuit, controls the servos, and works with the data processing areas. There are 5 major areas within the CD section. The laser pickup. The laser pickup reads the digitally encoded RF signal and sends it to the RF amplifier circuit. This is done by moving an objective lens up, down, left, and right with focus and tracking drive coils. In addition, it provides focus and tracking feedback error signals. The RF circuit. The RF circuit converts the digitally encoded RF signal into EFM digital data. This data is then sent to the servo and data processing areas. It also processes and amplifies focus and tracking error signals, which are used in the servo circuits. The servo processor provides the communications to the Mechacon interface, data processing interface, laser control, digital phase locked loop, and controls the 4 servo circuits. The servo processor controls 2 motors and 2 drive coils. The feed motor, also called a sled motor, steps the laser assembly forwards and backwards across the disc in small and large steps. The spindle motor, also called the disc motor, rotates the disc between 200 and 500 RPMs to maintain a steady EFM data transfer. The servo processor also drives 2 coils that shift the objective lens of the laser. The focus coil raises and lowers the lens, and the tracking coil moves the lens side to side. The data processor performs many processes. It demodulates the EFM digital signal, extracts the frame and block synchronization signals from the EFM data, extracts subcode data, performs deinterleaving error detection and error correction by using a RAM buffer, extracts and outputs left and right channel digital audio to the D to A circuit, and outputs many other timing and control signals. The D to A converter receives serial digital audio data from the data processor and separates it into parallel left and right channel digital data. It is then processed through a digital filter, noise shaper, and PWM generator. The PWM left and right audio are output from the D to A converter and sent through low-pass filters to recreate the original analog audio signal. We will now cover the servos, amplifiers, and driver circuits of the CD section, beginning with the focus circuits using the astigmatic error detection method. Many focus servos use a astigmatic error detection method. When the main beam reflects back from the disc, the shape of the returning beam changes from an ellipse in the AC direction into a perfect circle, then back into an ellipse in the B and D direction. Optimum focus is detected when a perfect circle is sensed. 4 photosensors, A, B, C, and D, are used to detect the returning main beam. The output of these photosensors are equal when the distance between the pickup and the disc surface is optimized. These photosensors are made into 2 pairs that produce a sum of the currents for each pair. Sensors B and D are added to produce 1 output, and sensors A and C are added to produce another output. Then we look at the result of subtracting the B plus D from the A plus C output. When the result of this subtraction equals 0, we have optimum focus. This comparison is usually made using an operational amplifier configured as a comparator. This gives us 3 possible outputs. When A plus C minus B plus D equals 0, this occurs when the returning main beam is round and evenly covers the areas of all 4 photosensors. This is also known as zero cross. When A plus C minus B plus D is greater than 0, this occurs when the ellipse mostly covers the areas of the A and C photosensors and the objective lens is too close to the disc. When A plus C minus B plus D is less than 0, this occurs when the ellipse mostly covers the areas of the B and D photosensors and the objective lens is too far from the disc. The astigmatic error detection method is performed by a focus error amplifier, which is usually made up of several operational amplifiers as shown in this circuit. The first pair of operational amplifiers are used to convert the currents from the 2 pairs of photosensors into a voltage. These 2 voltages are then compared to each other through the next operational amplifier. As we have learned, the output of the photosensors should produce 0 volts at the output of the focus error amplifier when the focus is optimum. To compensate for circuit tolerances, the focus offset adjustment is provided on one of the error amplifier inputs so that 0 volts is output at optimum focus. During normal disc playing, the output from the focus error amplifier, shown below, is sent to the focus driver circuit. This energizes the focus coil to move the lens up and down. As the lens moves, the focus error output will change and it will establish a servo loop. Before the focus servo part of the circuit is enabled, the CD logic performs a focus search. Focus search is used to find a starting point for the objective lens before the disc begins to spin. In addition, the focus search results can be used to determine if a disc is loaded or not. The focus search is performed by temporarily disconnecting the focus error output from the focus drive circuit. A slow oscillating ramp waveform is injected into the drive circuit's input that causes the objective lens to raise and lower smoothly. This ramp time is controlled by some RC constant that creates the ramp that takes approximately 1/2 second to rise once. It is so slow that you will have to slow down the time base of your oscilloscope to see it. Meanwhile, the output of the focus error amplifier is still monitored by the CD servo processor. When optimum focus is determined, the focus servo loop is reactivated to maintain focus, and then the disc will begin to spin. Here is the process for focus search. When a command to read the disc is given by the Mechacon, the laser diode is activated by the Mechacon or communicated and turned on through the servo processor. The servo processor outputs signals required for a focus search. During focus search, the servo loop is disabled. When the error voltage becomes minimal, close to 0 as possible, the CD servo processor will generate a focus OK signal, turn off the focus search, and activate the focus servo. Finally, the CD servo processor will start spinning the disc, and the focus servo will continuously maintain focus by sending the focus error amplifier's output to the focus driver circuit. RF circuits. The digital encoded RF signal is obtained from the main beam. Generally, the signal is picked up from the outputs of the current to voltage converters used in the focus error circuit and sent in a separate path. This signal is amplified by the RF amplifier. The RF envelope, called the I pattern, is used as a test point to confirm the RF level coming from the laser diode. This helps in determining if the laser is providing enough signal amplitude and if there is excessive jitter or instability. Because of disc surface vibration or servo errors, the RF signal is being biased by an unstable DC level. To read the data correctly, to distinguish ones and zeros, a slicer control circuit is used to ensure that the RF signal bias is stabilized. A comparator is then used to output distinct ones and zeros and are sent to the servo and data processors as the EFM signal. Tracking and feed circuits and servos. Before we cover the details about tracking and feed, we would like to define several basic concepts on their relationships with one another. During normal play, the tracking servo is used to move the objective lens side to side within the physical limits of the laser assembly. The range of the tracking coil is approximately plus or minus 40 tracks. When the tracking coil reaches near the end of its physical limit, an increase in tracking coil drive current is induced into the feed drive, which will advance the feed motor. When feeding across the disc in large steps to jump from one music track to another, the tracking servo is disabled and the servo processor advances the feed. The feed drive, or sled motor, is driven by two methods. The CD servo processor outputs feed drive signals for large steps across the disc, as in music track changes or during the initial feed to the home rest position. During normal play or while searching across a music track, the tracking servo induces a feed drive signal to move the pickup across the disc. Tracking. As you recall, the EFM data is being read by the main beam, which is also used for focusing. To keep this main beam on track, two sub-beams called E and F are used. As we have learned, the sub-beams are created from the main beam being split by the diffraction grating. They travel slightly ahead to the left and slightly behind to the right of the main beam. When the main beam is correctly on track, the outputs of the two sub-beams are balanced or equal. Here's a simulation of the beams tracking the pits. A tracking error detection method is performed when the two sub-beams are reflected back from the disc through the lenses and received at the two sub-beam photosensors. Any shift will cause the output of one sub-beam sensor to be greater than the other. These two sub-beams produce a current output, the same as the main beam, and lead and lag the main beam by plus and minus 12.8 microseconds. These two current outputs are compared and produce a tracking error output signal, which is fed back into the servo loop. This simulation shows the beams going off track. In this case, the E-beam is not hitting any pits and produces maximum current. As the objective lens moves off track in either direction, the output of the E and F sensors will produce one of three possible combinations. When the outputs from sensor E minus sensor F is greater than 0, the main beam is slightly to the left of the track. When E minus F is less than 0, the main beam is slightly to the right of the track. When E minus F equals 0 volts, the main beam is on track. Here is a diagram of the tracking error amplifier circuit. Similar to the focus error circuit, the current from the E and F photosensors is converted into a voltage. These two voltages are compared by the next operational amplifier to produce a DC voltage indicating which direction the tracking coil has to be driven. Because of circuit tolerances, there is a tracking offset adjustment which is used to balance the outputs of the E and F sensor circuits when the beams are at optimum tracking position. After the tracking error amplifier, the error signal is split into two paths. One goes to the tracking gain and drive circuits, and the other goes to the feed circuits where the large tracking errors can induce a feed. The tracking servo drive output is sent to the tracking driver. The driver energizes the tracking coil and moves the lens side to side. Large tracking drive outputs will induce a feed drive signal into the driver to advance the pickup assembly across the disc. Here is a typical tracking error signal which continuously drives the tracking coil and the feed motor to keep the main beam on track. There are other tracking gain drive signals which are used in the final stages of the tracking servo loop and vary model to model. They generally perform these type of functions. Initial tracking signal level adjustment. When the disc is initially started, the level of the tracking error signal can be sampled. If it's lower than expected, the CD servo processor, in some cases, can use amplifier gain control lines to bring the error signal up to acceptable levels. Tracking gain during normal play search operations, which stabilize the objective lens. During normal play operations, there can be other tracking gain control lines which are used for low and high frequency and phase correction. They're generally necessary after track searching, forward and backwards, or after physical shock detection and recovery. The feed sled circuits. Here is a block diagram of the feed drive circuit. The servo processor has a feed motor on control line, which enables a feed drive circuit, and a forward-backwards direction control. These lines go directly to the feed drive circuit for Mechicon-controlled feed operations as described before. Some units have a feed motor drive offset control which provides adjustment for circuit tolerances. During normal play operations, the inputs of the feed driver are enabled but idle. At this time, the tracking servo output induces the feed advanced signals. In this simulation, we can see the laser assembly being fed from the outer track to the inner track. And here is a typical feed drive signal during normal play. And during track search operations. The spindle circuits. The spindle motor drive circuit is used to maintain a constant rate of EFM data recovery from the CD. This requires the speed of the disc to change from about 500 RPMs at the inside edge to 200 RPMs at the outside edge of the disc. This is accomplished by the data processor detecting and recovering synchronization patterns that are contained in the EFM data stream. The PLL circuits used today have a wide and extremely stable capture and lock range. This digital PLL is built inside of the servo processor. The PLL uses a stable main reference clock to compare and maintain a 90-degree phase difference between it and the incoming EFM signal. The PLL produces a 4.3 MHz bit clock, which is used by the spindle servo drive to keep the disc spinning at the correct speed. If the rate of the EFM data changes, the bit clock will change and the disc servo responds by speeding up or slowing down the disc motor. The data processor receives the bit clock and the EFM data from the servo processor. It detects the frame synchronization pattern, which is the 2 consecutive 11T EFM patterns, and produces and outputs a 7.35 kHz frame sync. When you trigger your oscilloscope off the frame sync, you can clearly see the 2 11T EFM patterns. The spindle servo uses the bit clock and frame clock to synchronize and keep the frames of data coming in at the correct data rate. There are 2 modes used for operating the spindle servo. They are the pre-servo and main servo modes. The pre-servo. After the CD servo processor receives a focus OK, the spindle motor will quickly spin the disc up to a speed where the PLL can lock onto the EFM data. This is called the capture range of the PLL, and therefore a 4.3 MHz bit clock is produced as a reference for the spindle servo. Once PLL lock has been achieved, the main spindle servo is engaged. The main spindle servo uses 2 references to maintain correct disc speed and PLL lock. As we have learned, they are the bit clock and the frame sync. This main servo will vary the speed of the disc from about 200 RPMs near the outside to 500 RPMs at the inside, and maintains a steady data rate. This is called a constant linear velocity system, or CLV. The disc servo uses the bit clock and frame sync to produce 2 output drive signals for frequency and phase compensation. These pulse width modulated drive signals are 3-state drive outputs that can make the disc motor speed up and slow down. The drive signals are converted to DC voltages and applied to a pre-driver. The output of the pre-driver is then applied to the spindle motor driver circuit. Now we will look at the overall CD operation. Now that we have covered everything from basic CD formats to servo circuits, we will now summarize it all by going through the CD startup sequence. Most problems with repairs begin in determining what circuit could be at fault. Most CD players will follow this sequence of events to play a CD. There may be some subtle differences in the logic, but this flowchart will hold true. CD section power on. A standalone CD player will have power circuits that distribute power to all portions of the CD logic and drive circuits. However, in units that incorporate more than just a CD player, such as tape players, tuners, etc., will usually turn on the CD power circuits only when you select the CD player. These CD power circuits are usually controlled by the Mechicon and gets its power from the main power section. Therefore, do not assume that if the tape player or other circuits are working, that the CD section has power. This step is completed with the CD section powered and reset and waiting for further instructions from the mechanical controller. The next thing that occurs is mechanical reset and disk loading. This is performed by the mechanical controller and is affected by loading motors, switches, and photosensors. If the mechanical controller does not detect that a disk is loaded, the instructions to start the CD servo section will not be given. Once the disk is properly loaded, the mechanical controller will instruct the CD section to start. Many problems occur when one or more of these switches become defective, dirty, or intermittent. Because isolating these intermittent problems can elude the best technician, it is sometimes advisable to replace or inspect all of the suspected switches. The rest or home switch position. The CD servo section is instructed by the mechanical controller to move the pickup assembly towards the center of the disk. The pickup hits a switch called the rest switch that is momentarily pressed. The change at the rest switch is detected by the mechanical controller. If the rest switch is defective, dirty, or intermittent, the mechanical controller will not proceed to the next step and will give some form of error message. Now that the mechanical controller detected the rest switch and the disk is loaded, the command to turn on the laser is given to the CD section. The CD servo circuit will now produce a ramp signal that is input into the focus servo drive circuit. This ramp causes the objective lens to rise and fall smoothly and slowly to determine the best focal point from the disk. Depending on the logic of the unit, the objective lens will make 3 to 6 attempts to determine the best focal point. Generally, the pickup will usually find focus on the first rise of the objective lens. If focus has been achieved, the CD section will inform the mechanical controller that the focus is OK. The term focus OK is also referred to as zero cross. The mechanical controller program will probably shut the CD section down at this point if focus OK is not received. This is an added safety precaution. If focus OK has not been established, the disk will not be instructed to spin. This is what confuses many technicians who begin to troubleshoot the spindle motor circuit opposed to checking the previous steps outlined. The mechanical controller will instruct the CD servo circuit to spin the disk. This begins by rapidly bringing the disk up to speed so the disk can be read. The tracking circuit begins to produce an error output that drives the objective lens side to side to produce the least error. This means the laser is tracking a line of pits. Although the pickup is approximately at the inside edge of the disk, the exact position or groove is not yet determined. Now that the laser is tracking the line of pits, a RF signal is produced. This RF signal containing EFM data provides the synchronization patterns that the data processor detects. This synchronization pattern is used to adjust the spindle motor speed so the disk can be read. The table of contents is read from the disk, and the CD section now knows where the laser currently is and where all the song tracks are located. The CD section stops the disk and informs the mechanical controller what the table of contents information is and that it's ready for further commands. The next process depends on the program of the unit. The mechanical controller may sit and wait for the user to select a particular track, or it may begin to play the first track. The items we have just discussed here are the most important ones to remember. This is because you must think your way through this startup process for most repairs. Developing this practice will expedite the way you approach the repair.